In this video, I'm going to take up with the most important and crucial topic in electrostatics. Guess what? Yes, it is Coulomb's law. Coulomb's law forms the fundamental for nearly all the remaining topics in electrostatics. I am also introducing my book on electrostatics, a comprehensive guide that covers all topics in this unit thoroughly. With numerous diagrams and figures, I have explained various concepts in easy to remember manner. The book also includes a wide range of solved and unsolved numerical problems, providing ample options for a boards and for a competitive entrance examination. Coulomb's law. Coulomb's law states that the electrostatic force between two stationary point charges is directly proportional to the product and inversely proportional to the square of the distance between them. Let Q1 and Q2 be two charges separated by a distance of r. The electrostatic force acting on charge Q2 be F21 and the electrostatic force acting on charge Q1 be F12. The two forces F21 and force F12, they are equal and opposite. They have got equal magnitude. Magnitude of F21 and the magnitude of F12, they are equal and they are equal to F. According to Coulomb's law, the magnitude of the force between the two charges is directly proportional to the product Q1 into Q2 and inversely proportional to the square of the distance between them, 1 upon r square. Now, if any force is inversely proportional to the square of the distance, then that law is called inverse square law. That means Coulomb's law is obeying inverse square law. If you combine these two expressions, we will be getting F directly proportional to Q1 into Q2 upon r square. And when we remove the sign of proportionality, we keep a constant term. Epsilon naught is a constant term. Now here epsilon is called the permittivity of the medium in which we are keeping the two charges. Epsilon is called the permittivity of the medium. 1 upon 4 pi epsilon naught is a constant term whose value is 9 into 10 to the power of 9 Newton meter square per Coulomb square. Epsilon here is the permittivity of the medium in which we are keeping the two charges. If the medium is free space or medium is vacuum, then the permittivity is called epsilon naught, that is permittivity of free space. You can even remember one thing, that this Coulomb's law is named after a French physicist, Charles Augustin de Coulomb. SI unit of charge. SI unit of charge are coulombs. Now the question arises, how do we define 1 coulomb of charge? 1 coulomb is that much amount of charge which will repel equal and similar charge when placed at a distance of 1 meter in free space or vacuum with an electrostatic force of 9 into 10 to the power of 9 newtons. Here in this system we have two charges Q1 and Q2. Q1 and Q2 both are equal to 1 coulomb each. They are separated by a distance of 1 meter and they are placed in vacuum or free space. The electrostatic force acting on Q2, that is F21, and the electrostatic force acting on Q1, that is F12, both has got same magnitude but they are pointing in the opposite direction. In that case, magnitude of force here, this is equal to F. The magnitude of force F is 1 upon 4 pi epsilon naught. It is Q1 into Q2 upon r square. This is what we can get it from Coulomb's law. If you substitute the values, the value of 9 Now 1 upon 4 pi epsilon naught is 9 into 10 to the power of 9. Q1 is 1 coulomb, Q2 is 1 coulomb upon 1 meter square. That is force between the two charges will be 9 into 10 to the power of 9 newtons. Now this is how you define 1 coulomb of charge. Permittivity of a medium. Permittivity of a medium is a physical quantity that is determined by the ability of that medium to get polarized in response to an external electric field and thereby reducing the electric field within that substance. Or it can also be defined by one more way. Permittivity of a medium is a measure of the resistance that is encountered when forming an electric field within that medium. Now we can explain the term permittivity in some other way also. Suppose there is a neutral substance and we are keeping a positive charge near to this neutral substance. Now because of the presence of this positive charge near to this neutral substance, some charges will appear on the surface of this substance. The charges which appear are called induced charges. Here we are keeping one substance, we can name it as substance A. We can replace this substance A by substance B, then we can replace the substance B by substance C, then we can replace the substance C by substance D. So we can keep on changing different substances and we can place them at this place. Keeping the position of positive charge same, we will see that in all the substances, the magnitude of the induced charges will be different. In some cases, the induced charges are more. In some cases, the induced charges are less. Now here comes permittivity. Now the substances which can induce more charges on the surfaces has got more permittivity. The substances which are not able to induce enough of charges on the surfaces, they have got less permittivity. More the charges, more the induced charges, more the permittivity, less the induced charges, less will be the permittivity. Now we can take up first of all what will be the permittivity of free space. We have got different mediums, and in order to find the permittivity of a free space, we know that 1 upon 4 pi epsilon naught is equal to 9 into 10 to the power of 9. This epsilon naught is the permittivity of free space. Now by cross multiplication, epsilon naught will be 1 upon 4 pi into 9 into 10 to the power of 9. Now if you put the value for pi as 22 upon 7 or 3.14, we will be getting approximately 8.85 into 10 to the power of minus 12 Coulomb square upon Newton meter square. This is the value for permittivity of free space, which is minimum. And about the permittivity, one more thing is important. Now if you keep different charges in different mediums at the same place, so we will see that the electrostatic force between the two charges will be depending upon the medium, and they will be depending upon which property of that medium. They will be depending upon the permittivity of that medium. If the permittivity of the medium is more, then the electrostatic force will be less. The electrostatic force will be inversely proportional to the permittivity of that medium. Since permittivity of a medium is a physical quantity is that quantity which can be measured. If it can be measured, it should have some units and it should have some dimensions. So in order to find out the units of permittivity of the medium, we can use Coulomb's formula, which is F is equal to 1 upon epsilon naught Q1 into Q2 upon R square. By cross multiplication, epsilon will be 1 upon 4 pi F into Q1 into Q2 upon R square. The units of epsilon will be 1 upon force, 1 upon newtons, because 4 pi has got no units. 1 upon newtons, Coulomb into Coulomb upon 1 meter square. So we can say Coulomb square upon Newton meter square will be the units in which we can measure the permittivity of a given medium. Then in order to find out the dimensions, we can use the same formula. Dimensions of permittivity will be dimensions of 1 upon 4 pi f into q1 into q2 upon r square. 4 pi has got no dimensions. Force is m1 l1 t minus 2. Charge q1 q2 are both a1 t1 and upon r square l square. If you solve it, it will come out to be m to the power of minus 1, l to the power of minus 3, t to the power of 4, a square will be the dimensional formula for the permittivity of the medium. Relative permittivity of a medium. Relative permittivity of a medium is defined as the ratio of the permittivity of the medium to the permittivity of free space. Epsilon r is defined as the ratio of the epsilon upon epsilon naught. By cross multiplication, epsilon, the permittivity of a medium, is equal to epsilon r into epsilon naught. The same formula is shown here. We can even say that the relative permittivity is numerically equal to the dielectric constant of that medium. So we can even replace the relative permittivity by dielectric constant. Now there is one more thing which is important, that what are the values of relative permittivity? What is the minimum value and what is the maximum value? The minimum value of relative permittivity, minimum value of epsilon r is equal to 1. The minimum value is for vacuum or free space. The maximum value permittivity is infinity. It is for conductors. That means the relative permittivity will have a value between 1 and infinity. 1 is the minimum value and infinity will be the maximum value. All other mediums apart from vacuum and conductors, they will be having relative permittivity in between 1 and infinity. Now we had already done what is permittivity, then why relative permittivity is required? Now we had done the permittivity of a medium is equal to relative permittivity into permittivity of free space. Let us take up an example. Suppose there is a medium whose relative permittivity is 2. So the permittivity of that medium will be 2 times the permittivity of free space. It means that a medium whose relative permittivity is 2, the permittivity of that medium will be double the permittivity of free space. If we have a medium whose relative permittivity is 7, that means the permittivity of that medium will be 7 times the permittivity of free space. That means the relative permittivity of a medium is the physical quantity which will determine by what amount the permittivity of that medium will be more than the permittivity of free space. This is the physical significance of the relative permittivity. Since relative permittivity is a physical quantity, then it should have some units, it should have some dimensions. Now in case of relative permittivity, it has got no units, it has got no dimensions. Why? Because relative permittivity is a ratio of 2 permittivities. It has got no units and it has got no dimensions. Therefore, relative permittivity is a unitless and dimensionless physical quantity. Dielectric constant. Dielectric constant of a medium may be defined as the ratio of the electrostatic force between 2 charges placed at a certain distance apart in vacuum or free space to that of the electrostatic force between same 2 charges kept at the same distance apart in that medium. K, which is the representation of dielectric constant, it is equal to F air upon F medium, the electrostatic force between 2 charges kept at a certain distance apart in vacuum or free space to that of the electrostatic force between same 2 charges kept at the same distance apart but in that medium. If you put these formulas from the Coulomb's law, we will be getting some expressions and we will be getting finally permittivity of medium to the permittivity of free space. The remaining things will get cancelled. It can be easily shown that the dielectric constant is numerically equal to the relative permittivity of that medium. If you use the Coulomb's formula 1 upon 4 pi epsilon naught into epsilon r q1 q2 upon r square, we can replace epsilon r by k dielectric constant. The formula will become 1 upon 4 pi epsilon naught into k q1 q2 upon r square. Now there are few things which are important as far as dielectric constant is concerned. First, what are the different values it can have? Dielectric constant can have value between 1 and infinity. The minimum value is 1, which is for vacuum or free space, and maximum value is infinity, which is for conducting medium. All other mediums will have the values between 1 and infinity. Why dielectric constant cannot have a value less than 1? It means that we cannot have any medium whose permittivity is less than the permittivity of free space. The permittivity of free space is the minimum value of permittivity which any medium can have. Dielectric constant, as we did earlier, like relative permittivity, it has got no units, it has got no dimensions. It has got no units or no dimensions. That means it is a unitless and dimensionless physical quantity. Sometimes it is also known as SIC, specific inductive capacity. Now, dielectric constant of a medium is also the ability to concentrate the electric lines of force, and if you keep a given medium in an external electric field, if that medium is able to concentrate more electric lines of force, it means that the dielectric constant of that medium is more. If that medium is not able to concentrate enough of electric lines of force, it means that the dielectric constant is less. So dielectric constant of a material under given conditions is a measure of the extent to which it can concentrate the electric lines of force when that medium is kept in that electric field. The value of dielectric constant will be different for different mediums. Coulomb's force can be attractive or repulsive. It will be depending upon the nature of two charges, and it will be depending upon the product. If the product of two charges is positive, the force will be always repulsive. If the product of two charges is negative, the force will be always attractive. Now, why is it so? If the two charges are like charges, one positive, other is also positive. Positive into positive will be positive. Then they will be repelling each other because both are like charges. If both the charges are negative, negative into negative will again be positive. That means again it will be repulsive. Now, on the other hand, if the charges are unlike charges, one positive and one negative, positive into negative will be negative. They will be attracting each other because they are unlike charges. So one is positive, other is negative. Positive into negative is also negative. It means they will be always attract each other. It will be depending upon the product of the two charges. If the product is positive, they will repel each other. If the product is negative, they will be attracting each other. Factors on which the electrostatic force between two charges depend. According to Coulomb's law, the electrostatic force between two charges Q1 and Q2 separated by a distance of r is given by 1 upon 4 pi epsilon naught into k Q1 into Q2 upon r square. According to this formula, the electrostatic force depends upon four factors. First, the magnitude of the two charges. F is directly proportional to Q1 into Q2. More the magnitude of two charges, more will be the electrostatic force. Less the magnitude of two charges, less will be the electrostatic force. Secondly, it will depend upon the nature of the two charges, whether they are positive or they are negative. Like charges will always repel each other, unlike charges will always attract each other. Thirdly, it will be depending upon the nature of the medium in which we are keeping the two charges. The property of the medium which plays an important role is dielectric constant of that medium or relative permittivity of that medium. The electrostatic force is inversely proportional to the dielectric constant of that medium. Then last but not the least, the electrostatic force between two charges is inversely proportional to the square of the distance between them. F is inversely proportional to 1 upon r square. This expression is also known as inverse square law. Limitations of Coulomb's law. Although Coulomb's law is a complete law, which will be giving us an expression for the electrostatic force between two charges kept at a certain distance apart in a medium. But still, we can talk about some limitations of this law. First, the Coulomb's law is valid only for point charges. When there is a uniform distribution of charge, whether it is along a line, or it is on a surface, or it is inside a volume, then the total force acting on a given charge due to these charge distribution cannot be calculated straight away by using Coulomb's law. In addition to Coulomb's law, we have to use one tool, that is integration. Second limitation. Coulomb's law is valid only for stationary charges. When the charges are moving, then there will be a magnetic field around that charge. Then in addition to the electrostatic force, magnetic force also plays an important role. Third, Coulomb's law is valid only for two charges at one time. If you have a system in which we have more than two charges, maybe 3, 4, 5, in such cases, the total force acting on a given charge can be calculated by using one more additional tool like vectors. Without using vectors, such situations cannot be tackled. Such situations cannot be tackled by using Coulomb's law straight away. Although Coulomb's force, that is electrostatic force, and gravitational force, that is from Newton's law of gravitation, the two formulas for the forces are similar to each other, but there is a difference between the Coulomb's force and gravitational force. As it is clear that Coulomb's force or electrostatic force is in between two charges and the gravitational force is in between two masses. The electrostatic force is a very strong force as compared to gravitational force. Electrostatic force is 10 to the power 38 times stronger than the gravitational force. Gravitational force is always attractive. Every mass will attract every other mass, whereas the electrostatic force may be attractive or repulsive. Like charges will always repel each other, and unlike charges will always attract each other. The gravitational force is independent of the medium in which the two masses are kept, whereas the electrostatic force will depend upon the medium in which the two charges are kept. The gravitational force is a very long-range force. The gravitation pull of Sun will be extending till infinity. It will be extending to a very large distance. Whereas the electrostatic force is a very short-range force as compared to gravitational force. These are few differences between the Coulomb's force and gravitational force. Coulomb's law in vector form. Let there be two charges, Q1 and Q2, separated by a distance of r. Then F21 is an electrostatic force acting on charge Q2 due to charge Q1, and F12 is an electrostatic force acting on charge Q1 due to charge Q2. Before we could take up with the Coulomb's law in vector form, we have got certain terms which we are supposed to remember. If F1 is an electrostatic force acting on charge Q1 and F12 is an electrostatic force acting on charge Q1 due to charge Q2. Similarly, if F2 is an electrostatic force acting on charge Q2, then F21 is an electrostatic force acting on charge Q2 due to charge Q1. And R is the magnitude of the distance between the two charges Q1 and Q2. Then what is R12? R12 is a vector which is the distance between Q1 and Q2 starting from Q1 to Q2. From Q1 to Q2, if you go in this direction, R12 vector is pointing in this direction. Q1 to Q2. Then R21. R21 is the distance between Q1 and Q2 starting from Q2 to Q1. This Q2 to Q1, if you go in this direction, so this is R21. R21 is the distance between Q1 and Q2 starting from Q2 to Q1. Similarly, if it is R12 cap, R12 cap is a unit vector pointing from Q1 to Q2. And R21 cap, it is a unit vector pointing from Q2 to Q1. Now again, let there be two charges Q1 and Q2 separated by a distance of r. The electrostatic force acting on charge Q2 is F21 and the electrostatic force acting on charge Q1 is F12. According to Coulomb's law, the electrostatic force F is equal to 1 upon 4 pi epsilon naught k Q1 Q2 upon r square. This is a scalar formula for the Coulomb's law. If it is vector formula, then we have to give some direction. R cap is a unit vector pointing in the direction of force. The force is a vector quantity. It requires magnitude as well as direction. The magnitude is 1 upon 4 pi epsilon naught k Q1 Q2 upon r square and the direction is given by r cap. Then if it is to find out the force acting on charge Q1 due to charge Q2, that is F12 is 1 upon 4 pi epsilon naught Q1 Q2 upon r square R21 cap. F12 is pointing in the same direction as that of R21. R21 is a vector, unit vector pointing from Q2 to Q1. Similarly, F21 is an electrostatic force acting on charge Q2. Q2 due to charge Q1 is 1 upon 4 pi epsilon naught into k Q1 Q2 upon r square R12 cap. R12 cap is pointing in this direction from Q1 to Q2. These terms are important here. In this figure, let Q1 and Q2 be the two charges placed at the point A and B respectively in a plane where O is the origin, which is to be taken as a point of reference. R1 is the position vector of charge Q1 and R2 is representing the position vector of charge Q2. We are taking both the vectors with respect to point of reference O. The vector which is representing the distance between the two charges is R21. It is pointing from Q2 to Q1. And if it is R12, it is the vector which is pointing from Q1 to Q2. We can take up electrostatic force acting on charge Q2, which is F21. The electrostatic force acting on charge Q1 is F12. So you can see that F12 is pointing in the same direction of R21. Q1 and F12 are pointing in the same direction, and R12 and F21 are pointing in the same direction. So these are few terms which are important to be remembered when we'll take up with Coulomb's law in vector form. Now in the same figure, we can take up a triangle OAB. We can use triangle law of vector addition in this triangle, which states that when two vectors are represented by the two sides of a triangle taken in the same order, then the completing side of triangle taken in the opposite order will be representing the resultant. Here R1 plus R12 is equal to R2. R1 and R12 are the vectors which are taken in the same order, and R2 is the resultant. R12 can be written as R2 minus R1. Similarly, we can take up in the same triangle OAB. R2 plus R21 is equal to R1. R2 and R21 are the vectors which are taken in the same order, and in this case R1 is the resultant. R21 can be written as R1 minus R2. Now we can take up the expression for the electrostatic force acting on charge Q1 due to charge Q2, that is F12, which is 1 upon 4 pi epsilon naught Q1 Q2 upon R square R21 cap. R21 cap is a unit vector pointing in the direction of F12. R21 cap can be written as R21 vector upon R. So here we will be getting 1 upon 4 pi epsilon naught Q1 Q2 upon R cube, R1 minus R2. Similarly, the electrostatic force acting on charge Q2 due to charge Q1, that is F21, is 1 upon 4 pi epsilon naught Q1 Q2 upon R square R12 cap. R12 cap is a unit vector pointing in the direction of F21. So R12 cap can be written as R12 vector upon R. The final expression which we will be getting is 1 upon 4 pi epsilon naught Q1 Q2 upon R cube into R2 minus R1. So these are the two forms where we can represent Coulomb's law in vector form. Principle of superposition of electrostatic force. It states that the resulting force acting on a given charge placed in the neighborhood of number of charges is equal to the vector sum of the electrostatic forces exerted by individual charges on the given charge. Let Q0 be the given charge which is placed at some point, and Q1, Q2, Q3, Q4 are the other charges placed in its neighborhood. Then the resultant force acting on the given charge Q0, which is F0, is equal to the vector sum of the forces which are being exerted by the individual charges on that given charge. So F0 is equal to F01. F01 is the electrostatic force acting on the charge Q0 due to charge Q1. F02 is the electrostatic force acting on the charge Q0 due to charge Q2. F03 is the electrostatic force acting on the charge Q0 due to charge Q3, and so on. All these forces are to be added vectorically to get the resultant force acting on the given charge Q0. We can write down the same expression by putting the values. In place of F01, we can write down 1 upon 4 pi epsilon naught Q1 Q0 upon R1 square R1 naught cap. Similarly, F02 can be written as 1 upon 4 pi epsilon naught Q2 Q0 upon R2 square R2 naught cap. And if you just see, we can take 1 upon 4 pi epsilon naught and Q0 common. We'll be getting Q1 upon R1 square R1 naught cap, Q2 upon R2 square R2 naught cap, Q3 upon R3 square R3 naught cap. All these things are to be added vectorically. We can write down the same expression in this way: 1 upon 4 pi epsilon naught Q0 summation of I is equal to 1 to n Qi upon Ri square Ri naught cap. This is the resultant force. We can write down the resultant force acting on a given charge due to number of charges. We do have many numericals which are based on this formula, which are based on this concept, and this is something important.